Welcome to a session on how to do hybridization and electron configurations of elements on the periodic table. Before I talk about hybridization, I want to kind of review just how to do electron configurations of the elements, because I have a nice little PowerPoint that shows how to do the 1s2, 2s2, 2p business. So here in the S block, the first two columns in the periodic table are in the S block. And the top row is 1s, then 2s, and 3s, and so on. And as you know, that s orbitals can hold 2 electrons, so there are 2 columns in the s block. Now for our purposes, we're going to have to pretend that helium is part of the s block next to hydrogen. So now, with a p, the next one is the p block, and the p block, the lowest possible p is 2p. And after that, we get 3p, 4p, 5p, as you can see. So here's the p block over here, 2p, 3p, 4p, and so on. And you notice that there are 6 orbitals. There are 3 p orbitals. Each p orbital can take 2 electrons to give you 6 electrons, and that's why there are 6 columns. The next one is the d block, and there are 10 electrons possible in the d electrons possible. You notice that the lowest possible d is 3d. And by the way, you notice it comes after the 4s. That's okay. After 4s comes 3d. You notice that this is not the 4d, because if this were the 4d, there'd be something above it. Okay, and now the next one after this is the F block down below. There's the F block down below. And for the F block, we have your 4f and we have your 5f. And you notice that there are 14 orbitals, 14 electrons. Now for the F electrons, by the way, you notice that on your periodic tables that you have, you might find that there are 15 elements in the F block. But remember that one of them, by rights, belongs in the D block. If you have something that has 15 elements down here, it's because there's a blank over here, an empty space here. And you know you can't have an empty space, you have to actually have an element there. Okay. So let's do an example. We'll do the electron configuration of nickel. And in the Aufbau principle, you go up to and including the element. So this is where nickel is located in the periodic table. You notice that it's in the D block. We start with the S block, and the 1s row here has 2 electrons. So this is 1s2, and after this we have 2s2, 2p6. That gets you up to neon. Then after that you have 3s2, 3p6, 4s2, and then up to nickel will get you to 3d8. Go up to and including your element. Now 3d can have up to 10 electrons, but here we don't have enough electrons to completely fill the D shell. You can have fewer than a maximum number, but you cannot have more. So that's why nickel stops at 3d8. Okay, so that's for nickel. Now what happens if you have something a little more complicated, like iridium? Now for iridium, you could start all the way from 1s2, but that's going to be a rather long electron configuration. So we have what's called the condensed configuration, where you start with the last noble gas. In this case, the last noble gas is over here, xenon. To find the last noble gas, go to the element that you're doing the electron configuration for. Go up a row, and then go all the way to the right. And that noble gas is where you start with. So you start with xenon, and then you pick it up at 6s2. Remember, this is 1s, then 2s, 3s, 4s, 5s, 6s. So 6s2. And that'll get you to those elements, cesium and barium. After 6s2, be careful here, this is tricky. Go straight down to the 4f. Yes, I know I skipped this element over here. You'll pick it up later. So after 6s2, go straight down to 4f14. Remember, this is the lowest f you can have, which is 4. 4f, and just know there's 14 elements there. Don't bother counting them, you know there's 14. And then after that, pick it up and go up to the 5d. This is d1, d2, and so on, until you get up to the element d7. Okay, and that's how you do electron configuration. So that's a condensed electron configuration. And for the final exam, you're going to be expected to know condensed electron configurations. Now, for coinage metals, these follow their own rules. Let's go with copper to give you an example. The coinage metals, copper, silver, and gold, they do not follow the rules you would expect. Let's start with what you would expect them to be. Let's go for copper. This is what you would expect for copper. Go up, and then go all the way to the right, and you'll find your noble gas, argon. So starting from argon, 4s2, and then after 4s2, you go down to 3d, and 3d9. That'll get you to copper. That's what you would expect, but that's not actually what it is. Copper doesn't follow the rules. Instead, it's actually 4s1, 3d10. Watch what happened. One of the s electrons was sacrificed to complete the d shell, because nature likes complete shells. So that complete d shell, which is lower in energy, by the way, than the 4s anyway, is going to be completed at the expense of the 4s electron. So copper is going to have a 4s electron just hanging out there. So copper is argon, 4s1, 3d10. Now let's do it for silver and gold because they are analogous. Copper is argon, 4s1, 3d10. Now let's go to silver. Instead of argon, it's krypton. We go one noble gas down. Then 5s1, 4d10. So krypton, 5s1, 4d10. And then we go down to gold. Xenon, 6s1, 4f14, 5d10. That's for gold. Xenon, 6s1, 4f14, 5d10. You notice that for the gold we had to add the 4f14 still because we're past the lanthanides now. Okay? But they're all analogous in the sense that they all have that outermost 1s electron. And all three of them can form 1+ ions because they can lose that outermost electron. There are some others that don't follow the configurations. These are the others besides the coinage metals that break the rules. These will not be asked on the test. Okay, now let's go on to how electrons are actually filled in orbitals. When we do electron configurations, we just indicate the number of electrons as a number. But actually, we show the number of electrons, we can actually show a little bit more detail using what I call the boxes and arrows. Remember, there are 4 quantum numbers. The first one is the principal quantum number, n, with 1, 2, 3, 4, and so on. The second one is L, which we indicate by a letter, 0 for S, 1 for P, 2 for D, 3 for F. The third quantum number is M sub L, and that's indicated by the individual box. For S, you can only have 0. For P, you can have -1, 0, and 1. And for D, which is not shown, you would show 5 boxes in a row to represent -2, -1, 0, 1, and 2. Now, let's say that we wanted to do electron configuration of hydrogen. The last quantum number is M sub S, and that's +1/2 and -1/2. We indicate that with an arrow pointing up for +1/2 and an arrow pointing down for -1/2. Okay, so let's start drawing it. For a hydrogen, you would just show it like this, an arrow pointing up. And for simplicity, I'm just going to show the arrow with one head, half a head. And that would be for hydrogen. For helium, whose electron configuration is 1s2, we show the 2 electrons as 2 arrows. They're both in the 1s orbital, but they cannot be both +1/2 because that violates the Pauli exclusion principle. So we put one as +1/2 and the other one is -1/2 by drawing that as an arrow pointing down. Think of these boxes as like rooms, and the electrons are like students. They can take a roommate if they have to. They don't really like to, but they can take a roommate if they have to. And if they do take a roommate, they go to the registrar's office to get their spin flipped. Okay? The assistant dean actually does that. Okay. She flips your spin before you take a roommate. Now, if we have the third electron, the lithium, you cannot have more than 2 electrons in 1s. Remember that lithium's electron configuration is 1s2, 2s1. So we put the 2s over here, like that. And the 2s, and that gives you the third electron, 1s2, 2s1, and that's lithium. Beryllium, 1s2, 2s2. We've completed. So now we've got the element beryllium. Boron, 1s2, 2s2, 2p1. So how do we indicate that 2p electron? Go to the leftmost box and just put up an arrow pointing up. And that's boron, element number 5. 1s2, 2s2, 2p1. But for carbon, we've got a dilemma here. For carbon is 6 electrons, and we know its electron configuration from looking at the periodic table is 1s2, 2s2, 2p2. Where do you put that second p electron? Well, remember, these are like students. You're not going to take a roommate if you have a perfectly good empty room right next door. But if the next room is really far away, much farther away from your classes, you're going to just live with a roommate. But here we have a perfectly good empty room right next door, so that second p electron is going to go to the next room. It's going to be spin up. Now, Hund's rule and Pauli exclusion principle are not exactly the same thing. The Pauli exclusion principle tells you that you cannot have 2 spin up in the same box. That is absolutely forbidden. That's the Pauli exclusion principle. The Hund's rule is not as hard and fast as the Pauli exclusion principle. The Hund's rule lets you choose between configurations that are allowed by the Pauli exclusion principle. I could have taken that second p electron and placed it down here, and I wouldn't have violated the Pauli exclusion principle. This is still perfectly allowed in the Pauli exclusion principle. But it's not the lowest energy configuration. It's actually an excited state. The Hund's rule lets me determine which is the ground state. And the ground state, again, Pauli exclusion principle, I could just as well do this also and put it spin down in a separate box. But again, Hund's rule tells you put it in a separate box, but also spinning the same direction. That's the lowest energy configuration. And this would be for carbon. 1s2, 2s2, 2p2. When we go for nitrogen, guess where it goes? Right there. 1s2, 2s2, 2p3. When you get to oxygen and you put that fourth p electron in, now, well, Pauli exclusion principle again actually tells you that it's possible you could stick it way up here in the 3s, but it would rather not do that. Instead, we put it, flip it spin, have it go to the registrar's office to get it spin flipped, and then it's going to go down to the 2p orbital. It's not going to like it very much, having to live with a roommate, but it has that's the best choice for it. So this is oxygen, 1s2, 2s2, 2p4. Now, a term you need to know, diamagnetic and paramagnetic. Diamagnetic means that all electrons are paired. Paramagnetic means that one or more unpaired electrons, and that's paramagnetic. So if we have a paramagnetic compound, it has one or more unpaired electrons in it. This is oxygen, which has 8 electrons total, and you notice that 2 of them are unpaired, so that makes oxygen paramagnetic. So let's go here and delete some electrons. Go with nitrogen. Go back. This is nitrogen, which is still paramagnetic. Carbon, which is paramagnetic. Boron, which is paramagnetic. But then we get to beryllium, everything is paired, so this is diamagnetic. And of course, if we were to fill everything up and go all the way to neon, boron, carbon, nitrogen, oxygen, fluorine, all these are paramagnetic, but then when we get to neon, now it's diamagnetic. Go to sodium, paramagnetic, magnesium, diamagnetic. Okay. And as I mentioned here, this is just showing you the possibilities. The bottom four, the ones over here, 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 and here, these are allowed. These are all allowed by the Pauli exclusion principle. But this last one up here, this is not allowed. This is impossible. It violates the Pauli exclusion principle because of these two arrows that are inside the same box. Now, when we have the ground state and the excited states, these are all allowed, but Hund's only the ground state one, the one in green, is allowed by Hund's rule, because we have two electrons that are in separate boxes pointing in the same direction. So that tells you that that's the lowest energy state, and the lowest energy state is the ground state. And so we'll be focusing on the ground state. You can come up with any number of excited states, but there's only one ground state. Remember, when each box is singly occupied, then and only then do you start pairing. Now, we've talked about s and p and d orbitals. Orbitals are just probability functions that describe where you're likely to find the electron and where you cannot find the electron. Like, let's say you're looking for the professor. Let's say you're looking for your professor. There are certain places that you are more likely to find him, some places that you're less likely to find him, and some places you absolutely never find your professor. And the places where you never find an electron or a professor is a node. A node is the place where you won't find them. Okay? You'll be most likely to find your professor in the office. Maybe in the classroom, a little less likely. Maybe somewhere off on campus, a little less likely. But Cagney's nightclub, absolutely not. Okay, so same thing goes with electrons. We cannot determine exactly where the electron is going to be. So these are probability functions showing you the s electron. And you know, of course, you have your 1s, 2s, and 3s. And for our purposes, though, s electrons all have the same shape. They're perfectly spherical. They're the same in all directions. It's called isotropic. It's the fancy way of saying it. But and you notice that the only difference between a 1s, 2s, and 3s is size. And that is the only reason why atomic sizes get larger as you go down, is because the larger shells are larger in size. They can get farther away from the nucleus because they are higher in energy. That's the only reason why they get larger. But they all have the same shape. They're all spherical. You notice, and there's only one s electron in each shell. Now we have the p electron. There are three of them, and these p electrons can be pointing along three directions. There's a px, a py, and a pz. One pointing along the x-axis, one pointing along the y-axis, and one pointing up and down along the z-axis. Those are your p orbitals. Your d orbitals are down here below. You won't be expected to memorize the shapes of these orbitals, but just know that there's 5 of them, and they have a little bit more complicated shapes. And the f orbitals, there's 7 of them, and they're even more complicated still. And their shapes are so complicated that even inorganic chemists don't worry about them. But the ones that we'll be focusing on are the s orbitals and the p orbitals. Those are the ones whose shapes are important. Now you notice that, by the way, for the p orbital, one side is shaded and the other side is non-shaded. What this technically means is the sign of the wave function, whether the wave function that generated this orbital is positive or negative. That's a purely mathematical construct, though it has nothing to do with the actual charge of this. By the way, you notice another thing is that these p orbitals, they can take up to 2 electrons, but please don't be misled into think that one electron goes up here, the other electron goes down there. Even if they only had 1 electron, the electron would be occupying both lobes here. Now, we need to know about these shapes because of how the atoms make molecules. The s and p orbitals themselves do not actually make the bonds in molecules. Instead, the bonds are made by what are called hybridized orbitals. Now, you know, of course, you've heard of hybrids before, like a hybrid car is part gasoline and part electric, or a hybrid plant might be a form of two plants kind of mixed together. And that's kind of what this idea is here. That when a carbon atom makes a molecule, let's say methane, which is carbon and 4 hydrogens around it, there are 4 orbitals that are available on the carbon. You've got an s orbital and you've got 3 p orbitals. And the s orbital and the 3 p orbitals, they come together to make what are called sp3 hybrid orbitals. These are 4 orbitals that are 1/4 s and 3/4 p in character. And so they end up looking kind of like an s and kind of like a p. And they point along 4 directions, but the directions they point along are arranged in such a way that they're as far apart from each other as you can possibly get. Now, you can try this experiment yourself. You can take 4 balloons and tie them together in one knot, and they will naturally be 109.5 degrees apart from each other. This angle between here and here is 109.5 degrees. That's called the tetrahedral angle. And that's the shape that 4 things will take if they're points around a sphere and they have to be as far apart from each other as possible. Okay? So what this looks like is that each of these 4 lobes here connects to the s orbital on a hydrogen atom, and that's your bond. And the bond that's formed is called a sigma bond. Now, for the case of something like ethylene, which has a double bond in it, for ethylene, we make an s. We have our s orbital. We have our 1s, 1s2, 2s2, 2p2. That's going to be the electron configuration of carbon, and this is what it looks like if drawn out according to Hund's rule. We need to hybridize this, though. Now, before we hybridized all 4 of these orbitals, the 2s and the 1 2s orbital and the 3 2p orbitals. We hybridized all 4 of them to make sp3 hybrids. But we're going to see, though, is that one of the p orbitals has to remain purebred and stay there as just a 2p and not be part of the hybridization scheme. So the orbitals that are left to be hybridized are the 2s and 2 of the 2p orbitals. So they make an sp2 hybrid. So there are 3 of these as sp2 hybrids, and they're 120 degrees apart, as you can see down here. They're 120 degrees apart. Now, the p orbital that's left out of the hybridization scheme, that's going to be above and below the plane of the ring, and that's what makes the pi bond in ethylene. Now, I've showed this in class before, but let's just try this on the board here. If we're going to actually do the Lewis structure of ethylene, go ahead and take the carbon, take another carbon here, and we got the hydrogens here. I'll draw the hydrogens in here. And remember that we draw 4 electrons around each carbon because carbon is in group 4 in the periodic table. And 4 electrons around each carbon. And hydrogen's in group 1, so we only put 1 dot on the hydrogen. So we'll put 1 dot next to each hydrogen, pointing inwards because we know we're going to need it. We're going to need it to bond. Okay, and now we start connecting. I guess the first priority is to go ahead and connect that single dot bond on the hydrogen to something, so it has something to bond to. That's a single bond there. So now we've got these electrons that are available for bonding on the carbon. Here's 2, and then we connect together. to make one bond, and here's another 2 of them connect together to make the other bond, and that's how we know that it's necessary to have a double bond on the carbon. Now remember that when we have a double bond, the double bond is going to be a sigma bond and a pi bond. So going back to that hybridization scheme, we've got our 2s orbital and we've got our 2p orbital. They mix, they hybridize, but to make the hybridization, you have to reserve one of them as a purebred p orbital to make the pi bond down here. That makes the pi bond down here. And then the others can go ahead and make and hybridize. The s orbital and the other 2 p orbitals can hybridize to make sp2 hybrids. So the sp2 hybrids, they make the sigma bonds, but pi bonds are only made by pure p orbitals. Pi bonds cannot be hybridized. So this double bond in ethylene is a sigma bond and a pi bond. One sigma bond and one pi bond. Now when you put all these together, it looks a lot like a triple bond, but it's actually only a double bond. The sigma bond is in the middle in yellow, and the pi bond is in purple, above and below the plane of the molecule, and that only counts as one pi bond. So that's why this is a double bond. So whenever you see a double bond, think of that as a sigma bond and one sigma bond and one pi bond. If you have a triple bond, then it's going to be a sigma bond and 2 pi bonds. You cannot go above a triple bond. Quadruple bonds cannot be made except by involving d orbitals, and that only happens with metal-metal bonding, and that's beyond the scope of the course. So a single bond is a sigma bond, a double bond is a sigma and a pi, a triple bond is a sigma and 2 pi's. Okay, so let's look at some other things here. We've got, once we know about hybridization, sigma and pi bonds, we can actually go ahead and look at molecules and be able to determine how many sigma and pi bonds are located on this molecule. So first, let's look at the number of sigma bonds in the molecule. Remember that the sigma bonds, that each bond, single, double, triple, is one sigma bond. And then if you have a double bond, that counts as one pi bond, and if you have a triple bond, that counts as 2 pi bonds. And the reason why you need remember, a double bond only counts as 1 pi bond because you counted the first bond already of the double bond as a sigma bond. And the triple bond counts as 2 pi bonds because you have a total of 3 bonds there. The first one is sigma and the other 2 are pi. So let's count them in this little molecule here. We first count the sigma bonds. So count with me with the little green arrow here. This is count around the ring first, it's easier. 1, 2, 3, 4, 5, and then off the ring 6, 7, 8, 9, 10. That's the number of sigma bonds. There are 10 sigma bonds in this molecule. Now we'll count the pi bonds. The big double bond counts as 2 pi bonds, so that's 2. There's 4. Sorry, the triple bond counts as 2 pi bonds. 2, 4, double bond is 1, that's 5. Another double bond here is 1, that's 6. So 2, 4, 5, 6. So there's 10 sigma bonds and 6 pi bonds. Now if you count the total number of lines in this molecule, total number of bonds, 1 for sigma, 2 for pi, 3 for 1 for single, 2 for double, 3 for triple, and total number of bonds on the molecule, you should find there are 16. Yes, there are 16 bonds, but 10 of them are sigma bonds, and then 6 of them are pi. Okay, remember, count each bond as a sigma bond, and then if it's a triple bond, count it as 2 pi bonds. If it's a double bond, count it as 1 pi bond. 2, 4, 5, 6. Okay, Now once we know about sigma and pi bonds, we can use this to determine something called the hybridization of the molecule. Now I mentioned about sp3 hybridization and sp2 hybridization. And for sp3 hybridization, like for example with methane, the bond angle here, the angle between an atom connected here, the center, and another atom connected, is going to be 109.5 degrees. That's the tetrahedral angle. When you have three of them around the central atom, that's going to be sp2 hybridized. When you have three of them around, this is going to be 120 degrees. sp2 hybridized, that happens if you have one, if for example one of them needs to be a pi bond. And then sp hybridized, that's 180 degrees. Now, if you have more than four atoms connected, it's more than four things connected to the central atom, then we have to involve d orbitals because you run out of p orbitals. So if you have five things around, this would be an expanded octet. Then you have sp3d, and if you have six of them around, that's sp3d2. Let's look at an example of an sp3d. They show you the BRF3, for example, as an example of that. Let's go ahead and draw the Lewis structure of BRF3, just for fun. Let's see if we know how to do it. So I'll put the bromine in the middle, and I'll put the fluorines around it. And as I mentioned in class, drawing dots is difficult to do with a mouse, so I'm going to show a pair of dots as a horizontal line, which is also effective. I might do both actually, because if I might have to draw dots because why? Because I might have to split pairs up. All right, let's see if I can make this a little bit bigger. Can I do that? No, I can't. Okay, so here's BRF3. Now I'm going to go ahead and draw 7 dots around each one, because that's its valence electron count. So here's 7 dots around the fluorine. Remember, the line represents 2 dots. I know these pairs are not going to be split because it's fluorine. Fluorine is in that row that doesn't get expanded. Remember, on your periodic table, boron, carbon, nitrogen, oxygen, fluorine, neon, these things are never expanded. That's supposed to be a dot there. And then for bromine, I'll just go ahead and draw 7 dots. Okay, so the bromine has 7 dots around it. I can pair these two here, obviously. But then I'm stuck. I can't pair anything else. So to be able to pair anything else, I have to split a pair. So I'll just split the pair on the bottom. And once you split a pair, remember, once you split a pair, you have to do something with the other electron. So I split the pair on the bottom of the bromine so I could pair one electron with the fluorine. So I have to immediately go ahead and pair the other electron up as well. So what do we have here? We have a bromine with 2 lone pairs. I'll just connect the dots together to each other to show it as a lone pair. 2 lone pairs around it, and then 3 bonding pairs. So the bromine has 5 things around it. Now, when you're counting the number of things around the bromine, if we want to find out what the hybridization is on the bromine, count the total number of bonds, sigma bonds, plus lone pairs. Do not count pi bonds if there are any. Here there are no pi bonds in the molecule, just sigma bonds plus lone pairs. Okay, so for the bromine, when you're counting here for the bromine here, I've got one bond, 2 bond, 3 bonds, 1 lone pair, and 2 lone pairs. So together that makes 5. So 5 sigma bonds plus lone pairs. So that's the number I get. Now, if your total number of sigma bonds plus lone pairs is 2, this is going to be sp hybridized. If it's 3, sp2. If it's 4, sp3, if it's 5, sp3d, and 6, sp3d2. What if it's only 1? Well, the only thing that does that is hydrogen, and we don't worry about hybridization on hydrogen. Hydrogen doesn't hybridize, it's just S. Okay? So bromine is an expanded octet. It has 5 sigma bonds plus lone pairs, so this is going to be sp3d. Let's go to another example here, one that we drew in class, and that's sulfur trioxide. Because remember, the thing with sulfur trioxide is that there's more than one way to draw sulfur trioxide. Is that going to mess up our hybridization? Let's see. I'm going to try drawing it both ways. So here's sulfur trioxide. I'm going to go ahead and put in the lone pairs, put in the dots. There are 6 dots around each one because of where it is on the periodic table. There it is. And now I'm going to start pairing the dots. So let's pair the ones that are not paired on the sulfur first. Okay, so I've got a sulfur with 6 lone pairs, with 3 double bonds going around it. So that's one way to do sulfur trioxide. But there's another way to do sulfur trioxide. I'm going to redraw it here, and to save time, I'll just skip over to where it's drawn here. So here I redrew it now, but this time the sulfur only has 4 electrons, and I took away 2 electrons from the sulfur, so the sulfur now bears a 2+ formal charge. And the oxygens, I gave 2 of them 1 electron each. So 2 of the oxygens you see have 7 electrons around them, so they have a 1- formal charge each. And the third oxygen has 6 electrons, like it normally does. Now I'll go ahead and pair up the single dots here. Here, 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 and here. And you notice that I didn't have to split up any pairs on the sulfur. There were no pairs. So that means that I did not violate the octet rule. The octet rule stayed the same. The octet rule was followed. So does sulfur trioxide follow the octet rule or not? It depends on how you draw it. But what about the hybridization? Is the hybridization going to depend on how I draw it? It turns out the nice thing is that it doesn't. I go back a little bit here. Remember that for hybridization I'm counting sigma bonds plus lone pairs. Do not count pi bonds. So let's go to the first drawing here, and I'm going to count just the sigma bonds plus lone pairs on the central atom. It turns out that there are no lone pairs in the central atom, but I just count the sigma bonds. There are 3 double bonds sticking out of the central atom. Now remember, lone pairs, we're only counting lone pairs of the central atom. Don't worry about the outer atoms. Of course, they have lone pairs on them. Just the central atom. And so I have a double bond, so that counts as 1 sigma bond. I have another double bond that counts as another sigma bond, and here's the third sigma bond. So that's 3 things around this sulfur. That's 1 resonance. Now I try for the other resonance. Here's a sigma bond, because it's a single bond. Another sigma bond, which is a single bond. And this is a sigma and a pi, but I just count the sigma, so that's 3. So either way, you're going to get 3. And since there's 3 things around it, I go back and look at our chart here. That's going to be sp2. It's 3 bonds, 3 hybrids. 1 is going to be the s, the other 2 are going to be the p's. Pi bonds don't hybridize. They have to remain pure p's, so that's why we don't count them. Okay. And remember, if you have lone pairs, you count those too. Lone pairs are part of the hybridization. So again, these things around here, there's 3 sigma bonds and 2 lone pairs, so that's why there's 5 things around there. So that's sp3d for here. Now when it comes to bond angles, if you have something that's sp, sp2, that determines what the angles are going to be, 180, 120, and so on. Let's look at water for a second. For water, We put the lone pairs in here. O, put the Lewis structure in here. H. Water should be pretty easy, right? We put one thing around, one dot around the hydrogen, another dot around the hydrogen, and then for oxygen, 1, 2, 3, 4, 5, 6, and then we connect the hydrogen atoms to connect the hydrogens to make our bonds. And so we notice that the oxygen has 2 bonds and 2 lone pairs. 2 sigma bonds and 2 lone pairs. If one of those bonds had been a double bond, we would still count it as one bond, remember. So there's 2 sigma bonds and 2 lone pairs, so that gives you a total of 4, and so that means that this is sp3. If it's sp3 hybridized, it's going to have 109.5 degree angles. So the angle of this is 109.5 because that's the angle of that sp3 hybridization. Okay. We go over to the chart here, and that tells us that 109.5 is the tetrahedral angle, and that's characteristic of sp3 hybridized.